Good morning. Hope you guys are enjoying GTC. Welcome to this morning's talk. Olivier Maury from ILM, Industrial Light and Magic, is going to give the talk this morning. He has been with ILM since 2006. He's been in the VFX studios for over 13 years, holds an MSc in both theoretical physics as well as computer science. We're excited about this. We were just talking a little bit earlier. He actually did a talk on Plume about 4 years ago. A lot of things have been developed into it, and it's really progressed quite a bit, so I'm excited to hear this. We'll kind of cut it in about 20 plus minutes, and then we'll hold off for question and answers then. But Olivier, thanks so much.
Thanks, Michael. So good morning for those who came early. What is Plume? Plume is a GPU-based effects authoring tool that merges in a single step a fluid dynamics solver and a final quality volume renderer. So there's no I/O time associated to saving the grid as you're simming or loading it as you're rendering. So what I'm showing you right now is a sequence from Transformers 3 that heavily uses Plume, and this is for explosions, smoke, dust. To give you an idea, in the movie, there are thousands of Plume elements. Before Plume came online, we were typically running the overnight sim and then rendering afterwards. We wouldn't have been able to do that before Plume to produce these kinds of numbers. And to give you an idea, some of these shots have more than 60 or 70 Plume elements. This particular shot has about 30, and I'll go into details a little bit later in the presentation. In total, for Transformers, there were about 13,000 sim run for the show, and this is in a span of about 6 to 7 months of production. This one has this 420 had about that's the biggest one, 60 to 70 Plume elements. So as Michael said, it was introduced in production in 2009 for the last Airbender. And we were answering there to the mandate of being able to really accelerate the workflow and shorten the iteration time so that we could kind of converge towards what the director wanted for that show. And that was kind of these fire events, these fire elements that could be controlled and art directed in very specific ways. And so at the end of the show, it quickly became the main effects authoring tool for digital pyrotechnics, which is explosions, smoke, dust, these kinds of events. Since then, it's been used in 20 feature films and 2 Wright films, and this is the list. So let me tell you a little bit how Plume is unique compared to other tools, why we think it's unique. A lot of other tools that try to leverage the GPU to accelerate either the actual authoring process usually go for one module or maybe a few modules, maybe the pressure projection or the volume renderer, or maybe a specific expensive module in the dynamics. With Plume, we went for the whole thing. So the entire pipeline from A to Z is on the GPU, and the artist kind of inputs all its particles and sources, and gets at the end an actual final frame render. This is not a preview. It's usually either a rough version of a final quality frame render or a final quality. Development, so Plume is written entirely in CUDA, and development started in 2008 with CUDA 2.0. So for those who remember what that was, it wasn't always a happy place to be in terms of stability. So we chose a very consistent compute pattern. That was not the optimal. We knew it wasn't the optimal in terms of performance, the optimal compute pattern. So we didn't worry too much about memory coalescing and these kinds of things. And so we went for storing simulation data in linear memory and then reading back that data through the texture cache, through binding texture to linear memory. So this was a fairly good compromise for us. It was very simple to use in terms of development, and yet we had a lot of performance gains associated with it. Now, we discovered at some point that became an issue with the 12 gig boards, because running super high-res sims hit that threshold of the size of the linear memory, the texture that you can bind to linear memory. And so, but the NVIDIA folks helped us work around that problem. So let's focus now on the Plume solver. Plume is an Eulerian gas solver, fairly standard on a staggered grid. So pressure, velocity, and temperature. From the very beginning, we chose algorithms that are very amenable to the GPU. And for the pressure projection, we chose a multi-grid, a full geometric multi-grid, which is compared to there's the CPU counterpart, where you find more often a PCG, a conjugate gradient. The memory access patterns of a multi-grid are very local at every stage. So there's no reductions that you find in a PCG. So it's actually even, it's very, very nice on the GPU in terms of performance. It has drawbacks, which we'll see in the next slide, which is that it doesn't handle complex boundary conditions. For the advection step, we first started with an adaptive semi-Lagrangian and then moved quickly to a McCormick, which is what we use today. Which reduces the numerical dissipation. In terms of inputs, we have these three: the particle rasterization, which is very fast. We routinely pump 1 or 2 million particles per time step into the engine very, very quickly without noticing. Geometric primitives they get rasterized onto the grid that are modulated by some Perlin noise to break it up, and the Python source expression. So I'm going to go into more detail about this. Source expression really saved us on a number of shows because they're used in various ways. They allow artists to run a Python expression on the GPU. And this is a very clever piece of code written by Dan Peponi. So using the native mechanism of overloading and so method operator overload and decorators in Python, we were able to translate a full Python expression into an abstract syntax tree, then run the typical optimization that you run on an AST, which are like constant folding, dead branch elimination, and then translate that into bytecode that gets run into a virtual machine that's in a CUDA kernel. So that ended up, and this was done in 2008 or 9, and this ended up really going super fast. And as the PTX route, which was a kind of a parallel route that you could think of doing the same thing, it actually ended up being the right choice because the PTX compiling, the JIT compiling is actually really slow compared to this approach. So it's used for turbulence, for reheating. So because we're suffering, like any Eulerian solver, we're suffering from numerical dissipation. We could reheat locally. And on top of that, it was very artist-friendly. I'm saying ILM artist-friendly because at ILM, Python is the backbone of our pipeline. So these are expressions that you would find for any attribute, and it just so happens that this one gets translated and executed on the GPU. It was really nice to be able to shape exactly input fields the way we wanted. These are the other features. So I mentioned that the multi-grid didn't handle arbitrary boundary condition inside the domain. We worked around that using an IOP, the iterated orthogonal projection, which is a really nice algorithm that was published in 2009 by Moldmaker et al. That actually works around that problem. These are some of the other features in the solver that we have. Now I'm going to jump to the volume renderer. The volume renderer is a single pass ray marcher. It's a fixed shader, a hard-coded shader that takes as input ramps and a bunch of other parameters, but essentially ramps that artists use to map the simulated quantities to colors and opacities. So it's really intuitive for artists to play with that and not have to deal with code or shaders or even a fixed, usually some people choose a black body radiation profile, and it's kind of a static thing that you have to map gamma and things like that. One of the other key features is during simulation we had vec texture coordinate and we hook procedural detail at render time onto these texture coordinate, and that really allowed us to have really crunchy explosion cores, as you might have seen in the movies, as opposed to having to render, having to sim a very, very high res to get these crunchy detail. We were able to get them just at render time by a clever use of a procedural noise. It supports physically based lighting, single scattering, obviously, and multiple scattering through a diffuse approximation. So obviously, like any production renderer, It has to tie to the rest of the pipeline, and in terms of geometric integration, it's typically a deep buffer holdouts, deep output, deep shadow map input for the lighting integration this time. And this is for hard surface object to cast shadows onto Plume elements. And also the typical thing of splitting the components into different, we call them AOVs, arbitrary output variables, which are so fire, smoke, scatter, and I'll show you examples of that later. The last component of why Plume works so well at ILM right now is the GPU farm. So we have a dedicated compute farm of 128 Quadro FX 5800. These are 4 gig boards. They're getting old. They're like 2 or 3 generations behind, and we're thinking of upgrading this. They're actually Quadroplex 2200, so there's like 8 boards in each, so 2 Quadroplexes in each workstation, in each of the render farm machine. The scheduling is done through our award-winning software ObaQ. That's the CPU render farm scheduler. And we haven't really found an optimal solution to balance scalability and immediacy. I wrote interactivity. I should have said immediacy, because obviously there are ways to work with a GPU in terms of rendering and simulation. Either you have it's your main GPU that you're simming on, and then as soon as you sim, then your X server freezes, or you have your machine doesn't work as well as it usually does, or you have a second GPU, but then when you don't use that second GPU, it stays idle and it's useless. So we first started that route, and then we went for the full a GPU farm where people submit to the farm, but that means that there might be a pickup time associated to that. So it's not as immediate as the interactive, as the first 2 scenario that I was talking about. But we kind of reduced all the delays that are associated with pickup, and let alone some of the issues that we had about stability. And I'm really making it a point there that it's not a trivial thing to manage a GPU farm, because they're very early on, they were really, I mean, there still are from time to time, but there were really concerns about, obviously GPUs are not as mature as CPUs, so when they fall down, you have to reboot. I mean, there's a lot of things like that that are very time-consuming and laborious to put in place and converge progressively towards a robust solution. So there's health checks for the GPUs, their reboot schedule, making sure the X server is down, a lot of these questions. A lot of this work was done by someone called Ian Sachs. Did a remarkable job of making sure that we did converge at some point, especially during Transformers 3, where with these 13,000 sims. Now, as as Plume matured, we started building a library of setups that we call templates for different kinds of explosion, dust, smoke, sticky fire onto debris. And what originally was the mandate of raising the number of iterations so that we could converge quicker onto a small number of elements, of hero elements, became the ability of producing a huge number of elements with very few iteration, and that's what the templates realize. And I'm going to show you. So on the left side, you see this is the dialog box you see all these little postage stamp. An artist can actually click on one of them and get a movie of that template and see what it does if they create the setup. And on the right, there are 2 frames of 2 of the templates. So what I'm going to show you now, this is Xeno, our authoring framework. It's a video capture that's been sped up by a factor of 20. On the lower left, you'll see the artist checking quickly if the sources the particle sources are working. And this is one of the templates. It's called the fast explosion template. So they check quickly and they launch the sim, and this is what they see. Immediately the sim goes, and as the sim is progressing, they see a render going. And in this render, there's all the features. There's motion blur, deformation motion blur camera, multiple scattering. There are few lights. There's single scattering, obviously. So in a matter of minutes, they can check whether the sim is going well or not. They can cancel. After about 10 minutes of real time, this was about 30 seconds. After about 10 minutes of real time, this is what they get. This is a rough quality render, high quality sim, about 12 minutes, and it's 90 frames after 12 minutes. Now, if they had cranked the quality settings after an hour, this is what they get. And so a lot of the Transformers 3 elements, for example, were done in under an hour. And when I say under an hour, it's not one frame, it's the entire sequence. So I chose 2 frames of the previous sequences to show you the difference. The difference is actually not the simulation. The simulation is extremely fast. And what changes between the 2 is the rendering quality. So they're actually matched completely, and the difference is just noise. Out of curiosity, we ran this on a K6000, and the previous sim was a 65 million cell sim, and that was a 400 cube approximately. This is a 600 cube. It's a fairly high-res sim. We were very happy with the results. In 3 hours, you saw the render times. Effects artists working on water actually found it really nice and easy to use Plume for airflows. And this is a work that was pioneered on battleships. So the white water dynamics, as soon as it becomes ballistic, actually gets influenced by the airflow. And these are a few examples on battleship where everything over the water, all this cascade, the water cascade dripping from the ships are actually moving and influenced by a turbulent airflow. And it's all Plume. And this is in Star Trek Into Darkness. So I'm going to go through production examples pretty quickly. The first one is that Transformers shot of Optimus digging a hole into the building where the driller is kind of squeezing. I'm going to focus right now on the main explosion that you see. This is the input. This is just the input in terms of sourcing. There's nothing else. The big particles are temperature, and the smaller particle that you see swirling are velocity particles. So these velocity particles, and this is an insight that we gain after doing many tryouts in terms of authoring explosion. The velocity particles are tearing the field. They're actually picking up some high temperature and pushing it outwards and tearing the field. And that gives really nice turbulent tendrils. So this is the actual element on its own, rendered, and this was about an hour. It's worth saying that the artist working on this was very senior. It was a second take. Now, I'm going to show you all the other Pyro elements, and there I'll fast forward because there's a bunch of them. So there's about 10 Pyro elements here. Then I'll show you the dust elements. And those are just 2 of the types of elements that are in the shot. And there's another 10 here, so dust falling off, smoke. And here you see the deep shadow holdouts that I was talking to you about, where here, for example, here you see the driller that's held out of the actual element. This is one of these integration thing that I was mentioning, the integration features. So now let's move on to Avengers. This is a shot where Iron Man is chased by, I think it's called a Leviathan, yeah? Anyways, that breaks the side of the building, and it's a big dust cloud. Here on the opposite, where the velocity field is actually, there's no swirly velocity particles. They're just pushing the density particles that are more the contrasty particles here, the darker gray of the velocity. And we're just trying to have the fluid do its own thing and create its own natural swirls through incompressibility. So this is the rendered element. And then afterwards, you'll see single scattering. This is the OV breakup that I was talking to, and then the multiple scattering. And that compositing, this is the last stage of the pipeline, the artist can mix a little bit of both components to actually tweak it how they want. So now I'm going to move on to Battleship. This is a great example of a very simple setup. This is the typical setup, small particles velocity. The bigger particle at the stem are temperature, and it's the same concept of tearing. These are the elements that were rendered. These are some of the elements, because there are other elements that were the reflection part, the shadow, other plumes. this is an explosion. I put that in there to show you the different components, again, the different AOVs. So this is the explosion element. Now you'll see afterwards the fire bits, afterwards the multiple scattering, which is the influence of the fire onto the smoke, and then the smoke element. And I threw this one to show you when everything works well. This was done at the end of production. All the effects part was done in about 2 or 3 days. And this is all the element, the shock wave, the shooters, smoke shooters, the explosion elements, fire shooters, and at the end I think there's a miss pass. So in conclusion, Plume really changed the way we see digital pyro creation at ILM in terms of scheduling, in terms of bidding. For us, the combination of the high performance and the single step meant that junior artists could use Plume. So it opened up a whole new pool of artists, but also very senior but less technical people, more on the artistic side. And that also opened up a different pool. Overall, we think that the productivity increased by a factor of 10 thanks to that tool. So I'd like to acknowledge the following people who were instrumental in shaping Plume. And thank you very much. If you have questions, I'll be happy to answer. I'm going to roll a 2-minute reel. If you don't have a question, you can watch it.
We have enough time that we can run this, and then we got some time for questions.
So these are recent examples of how Plume was used, the Volcano, all the Volcano elements here on Star Trek. Explosions and it's kind of it goes back in time. It'll end by the movie that the Plume was created for, which was The Last Airbender. Do you guys have any questions?